All right, so 68B on page 145. Right away, James, I see the diagram, and I would think just draw the diagram on my sheet. So it looks like the first vector A comes straight down. So if I'm looking at a bird's eye view of the court, that's vector A straight down at no angle. Vector B is at an angle of 45 degrees. God bless you. It looks like it goes a little further than the height of vector A was, so maybe I'll keep going a little bit more. And then the next one is down at an angle of 30 degrees. Okay, so this is pretty much my diagram here. Imagine those lines are all straight lines, please, okay? So we have a person traveling across the court. Imagine the ball, actually, I should say, really. The ball is inbounded under the hoop. It's passed across the court. It's tossed down court to somebody else, and then this person maybe drives to the hoop, which is right here. So this is the path of the actual basketball, let's say. The thing about this problem is to recognize right away that one of your vectors has no direction, right? That's the part that's probably the trickiest, actually, out of this. In reality, it's actually one of the easier parts. This vector here, without an angle, you can't break it into components. These other ones, you could just use that method of components that we were talking about. But this cannot be broken into components. If I only move down, am I going in the X or the Y direction? If I only move down, which way is that? It's only the Y direction. So there is no X component for this first vector. So let's make our table. Okay, let's start with our table and think about what we're doing again. Along the top, we've got vector A, vector B, vector C. And then what do we need to do is we need to break them into pieces and then sum those pieces up to get the overall R vector at the very end. So we are looking for the resultant, we'll call that R at the end, and we're going to have to sum those together. And how do I find the resultant? Here's the beginning, the red dot. Here's the end, the other red dot. Just connect those two. When I connect these two dots, that gives me the actual resultant vector from A to B. Remember, the displacement is like the vector. I keep saying that, right? The displacement itself is a vector. If I'm moving right, that's positive 5 meters. If I'm moving left, that's negative 5 meters. Displacement is a vector because of the fact that it matters which way I go. The direction matters. A vector, direction matters. So the path along the black lines are like 3 shorter vectors, or like the distance. The direction matters for each of them individually, but the overall displacement from beginning to very end is drawn in red. So what are we really doing in this problem? We're breaking up all of these things into pieces. The first one is the easiest. I'm going to automatically put a 0 there because I know that this first vector is only drawn straight down. It's not drawn to the right, it's not drawn to the left, it's drawn straight down. So I know that the y is going to be negative something. What is that distance of vector A? Vector A is given as 10 meters. So that's simply going to be a negative 10 right there. Again, that's the length of vector A right there, 10 on the diagram. Is that clear, the first part? I'm literally looking at this figure and I'm saying to myself, which way is 10 pointed? If it's pointed in the X and Y direction, break the components up, which we're going to do for B and C. If it's only pointed in the Y direction, you literally only write it in the Y direction. If it were only pointed left to right, only write it here. Vector B, I have to look at, and that vector length is given as 20 meters. That's this one that's going diagonally across the court. And I have to simply remember the formula. This is where remembering it helps a lot, or just look at the formula sheet. It's on your formula sheet. We need to break that length of 20 into the base and height of the triangle that we make. So again, imagine, please, I'm not going to draw it on this one because I need you to start to visualize it more than me drawing it every time. Take this 20 right here and drop a height down from the top and think about extending the base across. This is the X component where I'm covering right now. And then this is the Y component. So I need to know what those pieces are. And if I forget, it's literally on your formula sheet right in the beginning. How do I find the X piece of a vector? What's the formula to find the X or horizontal piece of any vector? What do I use? I told you where to look, so if I don't see hands, I should see you all looking at your formula sheet, right? Kid, you got it already? Good, look then, that's fine. I saw your hand come up for a sec. So look for the horizontal component of the vector, or the vertical component, meaning like Rx and Ry. It's on your formula sheet. What do you got, Sophie?
It's vector cosine theta is equal to x.
Yeah, so for the x, so what's the vector length? You got to tell me what the numbers are, though, not just there, right? So what's the vector itself? 20. And then cosine of?
45.
Very good, the angle that it's drawn at. Why is that a positive value? Look at this vector that's length of 20. It moves which way?
Up and right.
Up and right. And up and right are both positive in x and y. So the right is positive for x, so this is positive, meaning I'm moving this way to the right. Then I have to move up to get there. So that's going to be a positive in the y also. What's the value in the y direction going to be? There's only one difference here.
Instead of cosine, it's sine.
Yeah, you still use the 20, and now it's sine 45. So you don't really even need the diagram. Notice, I'm purposely not drawing all these triangles in the diagram this time to show you the diagram is there to help you, but it's not necessary, actually. If I just remember to do this every time, just do 20 cos theta, or vector cos theta, vector sine theta, vector cos theta, vector sine theta. And then here, I got to know that it's 0 and 10 or whatever it is because of the way it's drawn. It's drawn straight down or straight up. It's only in the y. The last part, though, take a look. I'm gonna highlight this. Take a look up here, please. To get this third vector length c, which by the way is a length of 7 meters. This is a length of 7 meters. To move along that vector length c right there, I have to move to the right. So that's positive in the x. And then I have to move down. And down is, again, negative in the y. So I know that vector c is going to have a negative y component already. Because it's moving, again, follow vector c. You're moving right and down. Right is positive for x, which goes here. And then down is negative, which goes here for y. And you literally use the same thing you did for vector b, but except you use the other numbers now. So I've got 7 as my vector length. I know that the x is cosine, the y is sine. Right, so I start by putting the 7, then I put cosine and sine, and then just drop the angles there. The angles are 30 degrees. It's the same angle in both directions. And I'm using the angle that the third vector, vector c, is drawn with respect to the x-axis, which is 30. So this is literally an iterative method. You notice that? You're doing the same thing over and over and over and over and over and over and over again. So for those that understand how to do this, that are a little frustrated, I mean, not frustrated, but they're just waiting, it's good that you understand it. It means you've done enough practice. For those that are having trouble still, it means you need to practice this more. It's literally the simple solution to this kind of a problem, practice. Now, in addition to you practicing, it also means advocating. So look tonight if you're having trouble on this, because I'm gonna leave off once we finish this with this problem. We're gonna go back to chapter 3, because we've done a lot of chapter 4 lately, and I went over this in office hours today already. There are 3 more videos on Moodle explaining 3 further examples, actually 4 examples, because one of them actually other examples. One of them has 3 examples in it. So please, those are things that I recorded. Feel free to look at them. It might help you tonight to help to practice one of these. Now, what do I get when I sum the x components together? Remember, I'm summing these 3 together to give me whatever comes here. Summing these 3 together to give me whatever comes here. What do I get when I sum them? You got numbers? And? Yep, gotta take your time. Remember, guys, the negatives, don't forget the negatives, so the y direction.
10.6.
Negative 10.6? Or just 10.6? 10.6. Which makes sense. The diagram ends above where it started, right? Logically. So it should be positive. James is right, because if I look at the diagram, it looks like it ended above where it started. No, actually, it looks like it ended below where it started, right? If I start up here, James? According to the diagram, at least in the book, I kind of tried to copy it from scale, or by scale. Was it 10.6 for the y? What'd you get? Isabel, what'd you get?
I got
Negative.
no, I think I put in the wrong. I got 7.6, but I might put in the wrong.
Can somebody just verify the bottom line? Sum those 3 together? It may be 10.6. Maybe it ended up above where it started, but it seems unreasonable. James, you checked that you're back in degree mode?
I think they did 10.6.
Because, think about it this way, James, right? This is negative 10. This is another negative length down. This is not much going up. So I feel like the answer should be negative. So I don't know how these 3 could add up to 10.6. I feel like it's got to be negative. Is it not? But are others checking it? I need a verification or something.
I got like 0.6.
What'd you get?
I got like 0.6.
0.6? Okay, so that's what we need to talk, right? Because when you all start talking, we all can all agree. I have 2.6s, so I have a third. Nobody else got 0.6 as their answer? What'd you get, Will?
13.9.
13.9, doesn't sound right. What'd you get, Sophie?
I got 13.9, but I think
Can we hit mode? Hit mode, Will and Sophie. Both hit mode. Are you in degree or radian mode?
Oh, really?
You're in radian, Sophie?
yeah.
Go to degree mode and redo the problem. Ada, what'd you get? 0.6. I got 3 of them. Sold. 0. All right, it's 0.6. Why does that answer sound reasonable? Because think about it. We were saying a minute ago, it looks like this person didn't move very far up or down. So they just moved up a little bit above where they were. Like the smallest amount above where they had started. So when I'm looking at this answer, I'm looking at the red triangle here, really. So my drawing is really not as accurate as possible. And I was just sketching it based off what was in your book, so I don't know really where it was. So it looks like this ending, this last vector here, should have maybe only gone a little bit less, like maybe only to here. So that our resultant instead should have been this in blue. Okay, make believe the blue is our resultant now. The red is wrong. Okay, that was the original sketch. So this resultant is pretty much 20.2 meters to the right of where you look at the blue, please. Look at the blue. 20.2 meters to the right of where you started. And how far up? Only a little bit up. 0.6 meters up. These are the pieces of the right triangle that you now have to give yourself the resultant. Let me draw the right triangle. I'll draw it all in blue. It's really hard to draw this, sorry, because it's a long, slender right triangle. Imagine that's the right triangle. I know it's not drawn perfectly, okay, so just bear with me, please. So imagine that's where you ended up. This is approximately the right triangle that we're looking at here. Okay, we have a base length here of the right triangle of 20.2, a height of the right triangle of 0.6. It's a really slender right triangle. That's why this is annoying to draw. If I didn't draw it to scale, it would look like this. This is what I'm saying. This is 20.2, and this is 0.6. That is not to scale, though. I'm just drawing the triangle so you can see what I'm visualizing, okay? That's what you need to visualize. Because look, isn't 20.2 the sum of the x components? And that means right or left. 0.6 is the sum of the y components. That means up or down. So look at my triangle right here. That triangle is representing these two values. You need the resultant, which is always the hypotenuse. The process is redundant by now. It's almost getting old at this point. 20.2 squared plus 0.6 squared equals r squared. Our goal is to find r, the resultant. And then after that, we can find that little angle theta in there also. Okay, theta is drawn right in here. There's theta because I'm going 20 to the right and 0.6 up. That means that has to be theta. It's got to be northeast. I'm going right and up because these are both positives. What does r turn out to be? It's going to be very much like the answer of 20.2. It can't be much more.
Yes, 20.2, yeah, 21, so just 20.
It barely goes up, right?
Yeah.
Yeah, which makes sense. Think about a triangle like this. That's 20.2 across and only 0.6 up. It means the hypotenuse is not going to be much bigger than the base. And you can see that in the original sketch, really, right? Look at the original sketch. In the original sketch, here's the hypotenuse in blue. Here's the base in blue. Those are almost the same lengths, right? Because this triangle is so stretched out. So this resultant can't be much more than this number. So 20.21 is what Joe told me when he does 20.2 squared plus 0.6 squared all under the square root. How do I get an angle now here? I know it's northeast. I know it's northeast because I'm going right and up. How do I get an angle?
The tangent inverse of 12.6 over 20.2.
Well done, Will. The tangent inverse of y over x. Very good. Because if I look at my trig diagram over here that I just circled, I can see that clearly theta, or the tangent of theta, is equal to the opposite over adjacent. So tan theta is equal to 0.6 over 20.2 from this diagram right here. So Will's correct. Solve for theta, take the tangent inverse. What do you get, Will?
About
1.7 degrees? Yeah, it's a very slight incline. Very slight incline. Okay, because we said, look at the triangle in the original diagram. Look at how slim this is. This triangle is stretched out all the way along the x-axis. Here's your angle theta. I'm trying to point to it. I can barely even show. That's theta right there, between the two blue lines. That angle is tiny. That little angle between the two blue lines, That's why this is such a small number. Okay, again, this comes from this squared plus this squared equals r squared. Solve this for r using Pythagorean theorem. Let's go back to chapter 3 now, because we have a lot in chapter 3 on this test. The focus of this test is mainly chapter 3. Chapter 4, I would say, would be like, if I were giving proportions, I would say that chapter 4 is like 30% of the test, whereas chapter 3 is probably 70% of the test, okay? So that's why I really want to focus now on chapter 3. What was chapter 3 about, first of all? What was the whole topic called of chapter 3? There's one word to summarize the whole chapter. What kind of motion? Not constant motion, but motion that has what? What's the word when it's not constant velocity? It has what? Come on, vocabulary. If it's not moving at a constant velocity, it must be doing what? Good. So the word is acceleration. Chapter 3 is all about acceleration. Now, acceleration is, as we just said, defined as a change in velocity. That's why when I said, when velocity is not constant, you must be what? And Will said, okay, velocity is not constant, so that means he's saying that velocity is changing. When velocity changes, you have acceleration. Because the definition of acceleration is the change in velocity with respect to time. The change in velocity with respect to time. So that's the first equation that we started this chapter with, which was A equals delta V over delta T. Change in velocity with respect to time. We then jumped into 3 more formulas, which I don't have to really write all 3 out because they're on your formula sheet, right? VF equals VI plus AT. VF squared equals VI squared plus 2AX. Well, X equals VIT plus 1FAT squared. Those big 3 that I keep referring to, they're on your formula sheet. And they all say X. What kind of motion are you focused on when it says X? What kind of motion? Motion that is what? What's the word for left to right? What's the word?
Horizontal.
Thank you. And when it's vertical motion, what should I do with the variable X?
It turns to y.
Turns into the variable Y. It's the same 3 equations though. So if I'm moving horizontally on this test, you use the equations as written. If I'm moving vertically instead of X, you just put Y. It's the same thing though. Let's start with that statement so we're all clear. Okay, Joe.
So if it's the same thing, would it make a difference if you wrote X for like a vertical equation?
It doesn't matter. If you want to call it X, that's fine with me. But next chapter, you're going to get confused because we're going to really have to look at them separately.
Okay.
So I'm just trying to prompt you if you're getting ready for the next piece. But it is fine, yep. Now, one thing to know. If something is moving vertically, if it's dropped, what is it undergoing? Why is it falling physically, really? Why is it falling? What is it undergoing, Andre? Yeah, because of gravity. Gravity has an acceleration to it, right? What's that number? What's that number? Rodrigo?
-9.8.
Very good. Acceleration due to gravity on Earth in the y direction is negative 9.81 meters per second squared. This is on your formula sheet. I think I just write it with either plus or minus, or I just put A equals positive 9.81. Because you're going to see it that way later, where it says G, I think. This is the acceleration in the vertical direction we're going to always use. What if an object starts from rest? That's a key word and a key phrase we keep throwing out there. An object is dropped from rest. An object starts from rest. What do we have to make as a statement when we see that, Rick? Good. Let's jot that down. VI is 0. When is this? When it starts from rest. This is a key phrase that we're going to see a lot. We've seen it in all of the problems. If a problem says, how long does this occur for? What are we looking for? What are we solving for? Time. So I will probably not use the squared equation because VF squared plus VI squared, VF squared equals VI squared plus 2AX does not have time in it, right? So you remember how you choose the proper equation based on what you're given and what you're looking for. That whole concept is applying to this. Joe?
I just have a question because I know I brought this up before about VF. If in some problems, will it be 0 as opposed to other problems, or will it always have a value over 0?
If eventually, if the problem says, find the distance it takes for the object to eventually come to rest, then VF is 0, because it's coming to rest versus starting from rest, right? But if it says an object is dropped, and we're looking for the impact velocity, we are always looking for the value before it hit the ground, like the right before it hit the ground value.
Other than that, it says like it comes to...
It has to say comes to stop, comes to rest, or comes to a stop, or comes to a halt. But you're not going to see that right now because we are not looking at friction. When we get to friction, we're going to talk about why objects eventually stop, and VF has to be 0 there. And we'll see that.
There's only one problem on the problem set up. Like,
There's a problem that says
Okay, and does it give you initial velocity it started with?
Yeah.
And does it give you probably acceleration or time? One of those two? Or maybe distance, it gives you one of them?
Yeah.
You can do a problem where it comes to rest, for sure. That totally works. But we just haven't seen one of those just yet.
Yeah, that's all.
Okay? Yeah, but I could give you a problem on the test tomorrow, theoretically, that you could be able to answer with that if you want. To give you a sample would be like, and this is not on the test, but I'm just telling you off the top of my head. A car is driving and then applies the brakes. Find the deceleration if it goes from 40 miles per hour to 0 miles per hour in 10 seconds. Well, then you would just use that formula right there. Right? Vf minus Vi. With velocities, it takes 10 seconds. You could find the acceleration or the deceleration is what I asked for. So yes, you can find a solution when it comes to rest. Vf from V0.
Thank you.
Guys, good. These are good questions. That's the kind of stuff I want to hear. That means you've been looking at your stuff. Graphically, we need to understand the concept between the two different graphs. So let me go to a new slide for this. Look at those two. So we have position and time. Oops, that should be a T. And we have velocity versus time. So we've looked at these two graphs already. We saw them a lot in our first two labs, or our labs 2 and 3. We saw this with the picket fence lab and with the motion detector. And with the motion detector, it was really easy to plot the position graph. A lot of you did really well when you were just graphing where an object moves, right? So if I were to see a position graph of this, okay, so that's my position graph. Can we talk about the position of that object for a little bit? Can we tell a story about how that would be presented based on the graph alone? What's the person, and I don't need numbers. I'm not asking for numbers, just give me a story, because obviously there are no numbers. James, tell me what's happening.
It moved over a certain period of time, but then it stopped moving, but time kept going, and then it started moving again.
Now what happened here, James, when that's really steep?
It
It moved pretty,
fast.
yeah, it moved really fast right here. It accelerated, keep going.
Accelerated and then it stopped again.
So it decelerated then, right? And then it stopped. So let's use physics phrases as we describe it, okay? So for tomorrow, please, like the bowling ball example that was in one of your labs, I asked you to use the phrases acceleration, velocity, position, and a lot of you didn't. Use the correct vocabulary. So here, as James was saying, you would say, the velocity is constant because it's constantly moving away from the source. You could even say it started 3 meters or a certain distance from the source. Then it suddenly stops, which means the velocity is 0. Then there's positive acceleration causing it to get much faster. It's still increasing in position. And then it's negative acceleration causing it to slow down. And then it stops. So velocity is 0 and the rest. So I could easily tell a story based on that simple graph there. What would the velocity graph of that look like? Well, how would I draw a velocity graph given that? I would say, well, just let me find my slopes. So in the beginning, the slope is positive. Then the slope is 0. Then the slope is kind of really positive. It's still positive. It's getting less and less positive. And then it's 0. Oops. And then it's 0 again up here. There's never really a negative slope, if you notice, right? So a positive slope means a positive velocity. Then there's 0 velocity. Then it looks like the velocity started to get faster and faster, then slow down. Let me just point to where I'm saying this. Velocity was 0, 0, 0, ready? Then velocity got faster, faster, faster. And then velocity slowed down to 0. So it gets faster and then slows down. That would look like this. Okay, that's what this graph would look like for a velocity graph. And if I were to connect it properly, that's what it would look like. So this is the same thing if I tell the same story. The person moves with a constant velocity. Then suddenly they stop moving. That's the middle over here I'm at now. I could actually probably point to them together if I could, yeah. Then suddenly the person starts to increase velocity until they get to around there. Then the velocity gets a little bit less until eventually it's 0 at the end for both pieces. Does that make sense? Did that work, by the way? Could you see both pointers? Okay. So these are the same story told from two different graphs. Both graphs, though, again, they dictate the same idea because one is position, one is velocity. They can be different.
I don't understand why the first line, the first acceleration, and the second one are different in the graph.
Here?
Yeah.
Why is this one different from this one here?
No, why is the first one on the displacement over time, the first positive one, doesn't it stop on the first one? On the left, yeah.
Yeah, so it's got positive velocity for a while, right?
Yeah.
Because its position is increasing steadily. And then suddenly the position is no longer increasing, right? So you have to go from positive velocity to stopped, which is indicated right here from that drop in velocity. This should be kind of like a smooth curve in reality, Rodrigo. But because we're seeing a corner, see this is like a corner right here, it's not smooth. You can't really have a smooth deceleration, unfortunately. So it would be doing this.
But why does the second one goes?
And then why is the second one steady? Why is the second one like steadily going up and then steadily coming down instead of dropping dramatically? Because of the curvature there. We haven't really gotten into curvature as much, so I'm just trying to show you like little tidbits. See this curvature right here? See how this is like a steady increase in velocity? And then it's a steady decrease. Was this a steady decrease? This was just all positive and then suddenly 0. So you need the sudden drop. Whereas here, this was steadily becoming 0, right? So that's why it's steadily coming down. See how this is a drop and this one comes down a little bit slower? That's where you're seeing the curvature difference. It's a great question. Great question. Joe.
This reminds me of another problem that was on the problem set that I had a little trouble with.
Go ahead.
It was from 41, and it was on page 9.
Page 9.
No, I'm sorry, I think it was.
So this is chapter 3, number 41, right?
Yeah. It was the graph with like where it had time on the bottom and then velocity on top.
Got it. This is page 91 for those who are
Yeah,
looking
I was
at
just a
it.
little confused like about what it was asking for. Like,
It says the velocity time graph for an ice skater is shown in the following. So let me draw this real quick. And all I need to draw are my endpoints. Remember, I talked about how endpoints are all that matter. This is 2. This is 2. The next time is at 4. And that height is at 2.5. So notice what I'm doing, by the way. I'm only labeling the parts that matter. And then the next time is at 5. And that's at a height of 1. So that last point is going to be right here. So this is the graph that I'm seeing in this part. And it says for part A, what is the distance covered by the skater between 0 and 2 seconds, right? And then for part B, it says, how about between 2 and 5 seconds? So let's start with the first part. From 0 to 2 seconds, what's the distance covered is the question. So if I want to find distance, in this case, I think about the fact that this is my velocity, this is my time. So from 0 to 2 seconds, Joe, what's the initial velocity?
well, 0. Yeah.
Good, because at 0, it's 0. And then what's the final velocity? What would that be?
2
Meters per second, right? So, Joe's already given me 2 of the givens I need for part A. Because part A says, find the distance covered from 0 to 2. That's right here. That's this line. Now, I've got the initial velocity. I've got the final velocity. I'm looking for the distance covered. This object is only moving in that direction, meaning the velocity is only positive because the velocity is increasing. So when it says find the distance covered, I could really just find the displacement. Because if I'm only moving with a positive velocity, it means that I'm only moving this way, so the distance I cover is the same as my displacement. I haven't moved back. You follow me so far? So here I know that I'm looking for x. That's what I'm looking for here. I know my time interval is how long, Joe?
Oh, that's 2. Oh, so you would do the equation that gives you.
Absolutely. So I know the time interval is 2 seconds. So I would probably use, let's see, in this case, I would probably have to find acceleration first, which you do. And then after that, I would use this equation or the other one. So first find acceleration using this. Sorry, I'll write it in blue. So find acceleration using this. And that's VF minus VI over time. So there's your acceleration. Done in blue. Why did I do that? Can somebody answer that question? Why did I find the acceleration first? James? Correct. If I want to find x using that equation, or, remember, I could use that equation, or I can use the other equation, which tells me x equals VIT plus 1/2 AT squared. But for either of those equations to find x, Joe, I need time. I need acceleration. So in blue, I found the acceleration first, and then I have VF, I have VI, I have acceleration, I can find x. Or in the second equation down here, I have VIT, I have 1/2 AT squared, I can find x. I would probably use the second one because it's already solved for x. Would you agree with me?
Yeah.
Okay, so that's the answer for part A. Yes.
Question.
Yeah, absolutely. So that's how you get part A, just whatever that number turns out to be by plugging into the equation. Now, part B is a little bit trickier. I'll tell you right now, don't worry about part B for the test. Just because honestly, the fact you'd have to do 2 more parts, but to give you a simple idea of what you would do, Joe, you would do the exact same thing twice more. You would have to do it for this segment right here, Joe, because that's going to show that there's positive velocity. You could find VI, VF, and see what it is. And then, so this would be your VI, this would be your VF. Do that part. Then do it again for the next part. But now call this instead VI, and call this VF now for the second part that we're going to do in blue.
Basically, it's like building on itself.
Yep. Okay? You'll learn if you go on to take calculus that it turns out that, see how these are like little, if you draw from the x-axis, these are little shapes. See the shapes that are here if I did that? Joe? See those 3 shapes that I just drew? Yeah. If I drew these vertical lines here? In calculus, you'll learn later that the area under here is equal to the distance, actually. It's kind of a cool thing. The area, if you can calculate, which you can easily find that area. The area of this trapezoid, the area of this trapezoid, those are equal to those distances you would get. So that's a quick way to do it, but we haven't learned that. And that's something you learn like really in calculus a little bit later. So I'm teaching you the way to do it now based on what we've done.
Okay, that makes sense. Thank you.
Okay, good question, Joe. Very good question. Yeah, Rodrigo, go for it.
Back to the other graphs. How does the displacement over time?
The same one, or can I just hypothetically?
No, hypothetically.
Okay, go ahead.
How does the distance over time, displacement over time, has to be for the velocity to be?
For the velocity to be increasing, what should this graph look like?
Yeah.
Yeah, good question. Okay? Because think about it, ready? Here's what this is. This is parabolic growth. Parabola, right? Parabola or quadratic. You can think of it as an exponential if you want. It kind of looks that way. So what it means is this, right? Here we go. In the beginning, the velocity, remember it's always the curvature, it's the slope. So it's not much slope in the beginning, right? And then what happens to the slope? Follow my hand. My hand is the slope, right? The slope keeps going up, doesn't it? Until eventually, look how steep it is. Isn't it really steep? Remember, the slope of this graph is velocity. So what's happening is if I were to draw a bunch of slopes, there's the beginning slope. There's the next slope. There's the next slope until you're up here. And now look at the slope. See how much steeper it is suddenly? So because the slope is increasing, this would be corresponding to a graph that you just said, which would be a graph that would look like this. Those graphs correspond to one another. That's a great question he's asking right there, okay? If I think about velocity that's going up, it means that the slope or the curvature of my position has to keep increasing. Those little red tangent lines there are all slopes. And that's showing slope is increasing. And remember, the slope of the position versus time graph is velocity. Okay, the slope of position versus time is velocity. What's the slope of the bottom graph going to be equal to? What's the slope of the velocity graph? Who remembers? If my velocity is going up, why could that be happening? Only one thing could be causing velocity to go up. What is it? Acceleration. So the slope of this is acceleration. Slope of the velocity versus time graph is acceleration. And make sense of it. It totally makes sense. If you have a constant velocity, picture it. This is constant velocity. This is me walking across the room, one step at a time. Am I accelerating at all? No. And how would I graph constant velocity? It would be a velocity graph. It would be a velocity graph that looks like this. That's what constant velocity would look like. And what's the slope of that line? Everybody, what's the slope of that line? 0. So constant velocity really means 0 acceleration. That's constant velocity. So if you forget what the slope of each line means, think of it in terms of the problem. If I were to draw a graph like this, what does that mean? Okay, it means constant velocity, which means no acceleration. Oh, the slope is also 0. Therefore, acceleration and slope, those must be the same. And that's how you can remember what the slope is from this graph. So make the association in your head if you'd like to. Other questions? Keep asking, guys. These are good questions. I'm very, very happy with this. All right, let me ask you a couple questions, if you don't mind. So I'm thinking about types of problems that can be theoretical, right? So we've done a lot of math stuff. We've kind of worked on this math idea a lot. Theoretically, though, we talked about that table with slowing down and speeding up with velocity and acceleration. And we drew some major conclusions from it. So let me pose a question, maybe we can come up with that conclusion again. If I'm walking with a positive velocity, but there's negative acceleration pushing back against me, what am I doing? I must have to be doing what? So I'm walking this way, but suddenly the wind starts pushing this way. What's it going to do to me? It's going to slow me down. So when I have a positive velocity, yet a negative acceleration, I slow down. Agreed? So those signs are opposite, and I'm slowing down. Same thing occurs this way. If I have a negative velocity, yet acceleration is positive, pushing that way, I'm also slowing down, right? So what should we jot down as a conclusion there? What statement can we make? I mean, overall statement that I can write from what we just stated. Draw a conclusion from it. Nice.
If the sign of velocity and acceleration are opposite, then it's slowing down.
Exactly. When velocity and acceleration are opposite signs, you're slowing down. What do you think is going to be the case when they have the same sign? What are you doing? Speeding up. Okay? That's a general conclusion that we drew from that table. You have to understand how that works. Okay? If I'm moving this way, and suddenly, like, the wind pushes me this way, it's going to speed me up. It's going to make me go faster. It's going to make me go faster. I'm trying to think of other stuff that we haven't really gone a ton into. We've talked about vertical motion in class. Remember we looked at the graph of a billiards ball, a pool ball, tossed up and down. We looked at a graph of this to start. When I toss this object up, I'm giving it initial velocity, right? So it's got positive initial velocity here. The time it takes to the top is 3 seconds. How long will it take to get back down? Straight. You get a negative time. 3 seconds, good. So time up equals time down. That was symmetry. Remember we talked about that? If I throw this upward from the ground with a velocity of 20 meters per second, what's the velocity going to be when it returns to the ground? Sophie, answer this one again because you kind of did it before. Sorry, I didn't catch up. Right. What did she give as an answer before? If I toss it with positive 20 meters per second on the way up, it's going to be negative 20. That was a negative. So it'll be negative 20 when it hits the ground again. This is, again, assuming no what? You remember no what? Air resistance. You got to understand that, okay? I could show up as a theoretical thing. You got to assume no air resistance. That's the cause of symmetrical patterns in these products. At the very top of the path, what do we assume the object does?
Stops.
It stops. So if I want to find the time to the top of the path, or the distance to the top of the path, what should I set equal to 0? VF. Very good, Chris. Write that down. If that wasn't second nature, you gotta write that down. If you're looking for something to the top of the path, whether it be the time it takes or the displacement in the y direction to the top, set VF equal to 0. That's the key for those problems, which you won't be able to solve them. If you get the time to the top, though, as Sophie said, just double it to get the total time. Okay, just double it to get the total time. We talked about a lot with vectors. We did an example already. We should know that vectors are commutative. It doesn't matter the order in which you add them. You should be able to add vectors graphically if it's given on a graph. Right? If I'm given a graph with vector A like this, okay, if I'm given that's vector A, I know that vector A goes 3 units right and 9 units up. If I add vector B to it, and I know its length, I can see how far that goes up and over. So to get my overall resultant vector, capital R. I will try to do an example of this graph in the other class so you guys can see that version. Okay? Please keep studying chapter 3. Don't forget about chapter 3, please. Actually, do you have a pen by any chance? Because I don't have